Hey everyone, welcome back to my YouTube channel. If you are new here, I'm Junaid Dialis and today in this video we are diving into the one of the most important sorting algorithm in data structures and algorithm. It's quicksort. Sorting is a crucial concept in computer science and quicksort is widely used because of its efficiency and speed. In this video, we'll break it down step by step. So today we are going to talk about what is quicksort is and why it's important, how quicksort works with a detailed explanation, why quicksort is one of the fastest sorting techniques and real-world application of quicksort. By the end of the video, you'll have a clear understanding of quicksort and how it is used in real-world applications. So stick around and let's get started. So what is quicksort? Quicksort is a highly efficient and widely used sorting algorithm based on the divide and conquer approach. It was developed by Tony Hoare in 1959 and is one of the fastest sorting algorithms in practice. Quicksort works by searching a pivot element from an array, then rearranging the elements to the smallest elements are placed before it and larger element after it. This process is repeated recursively for the subarrays until the entire array is sorted. So let's talk about why is quicksort important in DSA. Sorting is one of the fundamental problems in computer science, and quicksort is a crucial algorithm for multiple reasons. It's an in-place sorting algorithm, meaning it doesn't require extra space. It performs well in real-world applications and is used in standard libraries like C++, Java and Python. Compared to other sorting techniques like bubble sort or insertion sort, quicksort is much faster with an average time complexity of O(n log n). It is used as the base of hybrid sorting algorithms like Introsort, which is implemented in many programming languages. Step 1 is to choose a pivot. The first step in quicksort is selecting a pivot element. The pivot can be chosen in different ways: the first element, the last element of the array, or randomly selected element, or median of 3 method. Choosing a good pivot is important to avoid worst case performance, which happens when the array is already sorted. And the second step is partitioning the array. Once the pivot is chosen, the array is rearranged so that elements smaller than pivot go to the left, elements greater than the pivot go to the right. This is done using two pointers, a left pointer that moves forward until it finds a value greater than the pivot, a right pointer that moves backwards until it finds a value smaller than the pivot. The two values are swapped and this continue until the pointer cross. At the end of partitioning, the pivot is placed in the correct position and the array is now divided into two subarrays. Step 3 is recursively sort the subarrays. Now quicksort is applied recursively on the left and right subarrays. The same pivot selection and partitioning process is repeated on each half. This continues until each subarray has only one element. And the step 4 is base case. The recursion stops when the subarray are reduced to single element or an element array at the point. At this point, all elements are sorted and the algorithm is completed. Let's do an example in quicksort. Now this is an unsorted array. Let's take the pivot as 3. K will iterate over the array. I will track the boundaries for the smallest element. Now let's start by partitioning the array. Start with I equal -1 and k equals 0. Check each element with the pivot 3. Now k equals 0, element is 4, which is greater than the pivot 3. No swap, just move to the next k. Now k equal 1. Element is 2, which is less than the pivot 3. Increase I to 0 and swap elements at I equals 0 and k equal 1. Now the new array is 2, 4, 7, 5, 1, 6, 3. K equal 2. Element is 7, which is greater than the pivot 3. No swap, just move to the next k. K equal 3. Element is 5, which is greater than the pivot 3. No swap, just move to the next k. K equal 4. Element is 1, which is less than the pivot 3. Increment I to 1 and swap elements at I equal 1 and k equal 4. Now the new array is 2, 1, 7, 5, 4, 6, 3. Now k equal 5. Element is 6, which is the greatest than the pivot 3. No swap, just move to the next k. Now the k equals 6. Element is 3, which is equal to the pivot. No swap, just move on to the final partition step. Swap element at I plus 1 equal to and k equals 6. Now the new array is 2, 1, 3, 5, 4, 6, 7. After partitioning, pivot 3 is in its correct position and index 2. Now we have divided two arrays like left part 2 and 1, right part 5, 4, 6, 7. Now let's proceed with sorting the two sub-arrays. Step 2. Sorting left part. Let's take the pivot as 1. Start with I equal minus 1 and k equals 0. K equals 0 element 2 is greater than the pivot 1. No swap, just move the k. Swap the elements at I plus 1 equals 0 and k minus 1. Now the new array is 1, 2, 3, 5, 4, 6, 7. The left part is now sorted. Now let's move on to the right sorting part. Let's take the pivot as 7, the last element of the array. Start with I equal 2 and k equal 3. K equal 3 element 5 is less than the pivot 7. Increment I to 3 and swap elements at I equal 3 and k equal 3. No changes. K equal 4 element 4 is less than the pivot 7. Increment I to 4 and swap the elements at the I equal 4 and k equal 4. No changes. K equal 5 is less than the pivot 7. Increment I to 5 and swap the elements at the I equal 5 and k equal 5. Swap the pivot 7 with the element at I plus 1. Index is 6. Swap elements at I plus 1 equals 6 and k equals 6. No changes. The right part is now divided into left part and right part. The right part is already sorted. Now let's sort the 5, 4, 6. Let's take the pivot 6, the last element. The array before partitioning is 2, 1, 3, 5, 4, 6, 7. Start with I equal 2 and k equal 3. Let's walk through the partitioning process. K equal 3, element 5 is less than the pivot 6. Increase I to the 3 and swap the elements at I equal 3 and k equal 3. No changes. And k equal 4. Elements 4 is less than the pivot 6. Increment I to 4 and swap elements at I equal 4 and k equal 4. No changes. Now swap the pivot 6 with the element at I plus 1. That means index 5. Since the pivot is already in the correct position, no actual swap is needed. Now the array remains 2, 1, 3, 5, 4, 6, 7. Now we have left part and right part. The left part is 5, 4 and the right part is 6. All 6 is already sorted. Now let's sort the 5, 4. Let's take the pivot 4. The array before partitioning is 2, 1, 3, 5, 4, 6, 7. Start with I equal 3 and k equal 4. K equal 3 element 5 is greater than the pivot 4. No changes. Move to the next k. Now swap the pivot 4 with element at I plus 1. Array becomes 1, 2, 3, 4, 5, 6, 7. Now the array is fully sorted and the final result is 1, 2, 3, 4, 5, 6, 7. Let's move on to the code explanation part. So I have written a Java code in Apache NetBeans. In the first 12 to 32 lines, we have written the partitioning part. The core of Quicksort is partition function. This function places the pivot elements in its correct position in the sorted array and arranges the other elements around it. Here we first pick the last element in the array as the pivot. The goal is to ensure that all elements less than the pivot are placed before it and all elements greater than it are placed after it. We use a pointer I to keep the tracker of where the place smaller elements. When we find the element smaller than the pivot, the swap is with the element at position I. Once the loop finishes, we swap the pivot with the element at position I plus 1, replacing the pivot in its correct position. Now let's move on to the quicksort function. Line 35 to 45. The quicksort function is checks if the low index is less than the high index. If so, it calls the partition function place to the pivot in correct position. It then recursively sorts the sub-arrays before and after the pivot. The recursion continues until the base case is reached, where low is not less than high, meaning the sub-array is already sorted. Now to the main function. Line 46 to 55. In this main method, we initialize an array of integers. We first print the original array using the printArray method. Then we call quicksort to sort the array passing in the entire array, range from index 0 to ARR length -1. Finally, we print the sorted array. Now to the helper function. Line 59 to 66. This method simply loops through the array and prints each element followed by a space, then moves to the new line after printing all elements. And this is the output. Let's look at the time complexity of quicksort. The best case is when the pivot splits the array into nearly equal halves, leading to balanced recursion. Average case is when on random data, quicksort efficiently divided and sorts elements. Worst case occurs when the pivot is always the smallest or largest element, leading to unbalanced recursion. Space complexity due to recursive calls in the stack. Now let's talk about why quicksort efficient. Quicksort is one of the most efficient sorting algorithms because it has an average time complexity of O(n) log n, which is the fastest than most other comparison-based sorting algorithms. It works well for large data sets, making it more practical than bubble sort, selection sort, or insertion sort. It performs well with cache memory because it uses in-place partitioning, reducing memory overhead. Let's look at the real-world applications of quicksort. Quicksort is not just a theoretical algorithm. It is widely used in real-world applications like database systems, e-commerce websites, operation systems, file systems, and machine learning and big data. To summarize, the quicksort is a fast, efficient, and widely used sorting algorithm. Based on the divide and conquer method, it is important in EDSA, has a well-structured process, and widely used in real-world applications. If you are preparing for coding interviews or competitive programming, understanding quicksort is a must. Hope this video helped you to understand quicksort. Don't forget to subscribe, like, comment, and share. See you in our next video.